to this dynamic programming algorithm. Okay, so so the ordering heuristics are just basically kind of common sense rules that are applied, that are used to constrain the search space a little bit. And then the dynamic programming algorithm is the way we're going to explore the entire search space. So the heuristics are pretty simple. Okay, so the first heuristic is push down all filters. Okay, so if I have a selection in my query and the cylinder optimizer, we push those selections down as far as we can in the query plan. We apply them before we do any joins. Okay, and this is kind of a common sense thing that says, look, you should reduce the relations as much as possible before you access them. In general, this is probably always a good rule, unless for some reason these filters are really expensive, like they're doing some complicated analysis of the data set, right? So if you had some, database systems allow users to write their own or specify their own predicates. So these are like, image search functions or something that scan through an image that's stored in a binary object type inside of a database, then pushing down filters might not be a good idea. But generally speaking, for the kinds of filters that we mostly talk about in this class that are like range predicates over, integers or numbers, it's going to make perfect sense to push these down and apply them as early as possible. So this does constrain the search space because now we don't have to figure out how to interleave these filters in with the join operators. Okay, so the second thing that we do is, what I mentioned last time, is these consider left heap only plans. Okay, so this is the kind of a fairly big restriction in Celinger. So left heap only, remember, means that the right side of every join is going to be a base relation. Okay, so we would, for example, Celinger would consider this plan, but not this plan. This is not a left heap plan because on the right side of this join, there's something that's not a base relation. Okay? And we'll talk about in more recent, this sort of is a limitation only of the Celinger algorithm. You can go read about how to fix this to make optimizers able to consider bushy plans as well. It increases the complexity of the algorithm a little bit. And then the third one is no cross products. Okay. So that is to say, if I'm joining A, B, and C, I would never consider joining, if there's not a join predicate between A and B, then I wouldn't ever consider joining them directly, right? So I only consider joining relations that are actually, have a join predicate between them, right? So even though it would be a valid thing to do to say join A and B if there's no join predicate between them and compute the cross product and then join that with C, that's a legal evaluation of the query plan. It doesn't necessarily, it probably doesn't make sense to ever enumerate it to actually, compute a cross product. So we just say we won't consider these. It's a little bit, this no cross products thing it's hard to sort of figure out how it figures into the complexity of the algorithm because, whether it affects the complexity of the algorithm or not depends on the number of such, the number of join predicates that appear in a given query. So the algorithm is basically going to have runtime here. Instead of it being n is the number of relations, it's going to be n is somehow proportional to the number of join expressions that appear in the query. But anyway, this is just a good common sense rule. Okay, so those are the heuristics. So we apply these. And these heuristics, the one thing that these heuristics do, if you look at these parenthesizations, is you can see that this left heap only basically means that we're only going to consider plans that sort of look like this, right? So left heap only plans will always have this kind of structure, something that sort of looks like this, okay? And so that means that we only have to consider one parenthesization. So actually this funky expression that we said here about the number of possible parenthesizations of the plans doesn't really matter. We're just concerned with this n factorial thing, which is the number of possible orderings of these relations. And we don't have to worry about the parenthesizations because this left heap is there's only one possible parenthesization with the left heap plan. Okay, everybody cool so far with the setup? Any questions? All right. Okay, so now let's get into how the dynamic programming algorithm works. So those of you who've seen dynamic programming before, many of you have probably been exposed to it. The key idea is to identify some sort of optimal substructure in this problem. Okay, so the idea with dynamic programming is that we're going to be able to compute smaller subproblems and then reuse the results of those smaller subproblems in order to compute the larger answer. Okay, and our smaller subproblems in this case are going to be joins of, if I'm joining n relations, I'm going to figure out how to optimally join fewer than n relations, and I'm going to then reuse those optimal plans for those smaller numbers of relations in computing the larger relations. Okay, so the kind of key observation is that suppose I have this set of relations A, B, and C. Okay, and I haven't told you anything about I don't yet know what the optimal way to order them is. But suppose I compute that the optimal way to order them is the optimal plan for these is to first join A and B and then join that with C. Okay, suppose I say this is the optimal plan. So this is a set of three relations. This is the optimal plan for joining those. Okay. Now, if you think about taking this set ABC and joining it with some additional relation D, right? Then if ABC is the optimal, then the optimal way to join A, B, and C doesn't have anything to do. It's still the optimal way to join A, B, and C, even once I join that in with D, right? It doesn't change anything. The best way to join A, B, and C doesn't change when I add D into the mix, right? So what we can do is we don't need to reconsider this problem of computing how to join A, B, and C when we're considering how to join A, B, C, and D. Okay, so I'm going to be able to exploit that in the algorithm that we develop. Right? And that statement that I said is mostly true. There's a little caveat that comes out, which is that if you think about, so suppose I've got this set A, B, C, okay, and I'm going to join this. I want to figure out how to join this with D. So there is one little issue, which is that the optimal way to join D in with this set may be different if I can produce the output of this join in the same sorted order that D is in, right? Because if I can apply this merge, if I can apply a merge join without a sort, then I may be able to kind of get away with, I may be able to find a faster algorithm. So the sort of presence of D could actually affect the best output for A, B, and C. We're going to come back to that consideration at the end. The paper talks about this, they present this notion of interesting orders, and basically the idea is that in addition to computing the optimal way to compute A, B, and C, we're going to maintain the optimal way to join A, B, and C that produces data in some ordering that might be useful later in the query plan. But we'll come back and talk a bit about that in a minute. So for now, don't worry about that case. Let's just think about doing nested loops joins or something where ordering doesn't matter. Okay. Yeah. Okay, great. So that's the next part. So you're right that it might have been better to join, to do A, D, B, and then join C to that or something, right? So in fact, what we need to do, right? So although it's true that the optimal way to join A, B, and C doesn't really it's still the optimal way to join A, B, and C, if I'm adding D onto the end of it. The optimal way to join all four of these, right, might be to join, mix D into it, right? So when I'm considering the optimal way to join A, B, C, and D, what I'm going to do is I'm going to consider, I'm going to take all the size 3 subsets of A, B, C, D, right? And then I'm going to consider the optimal way to add the fourth relation onto that. Right? And because I'm doing dynamic programming, what I'm going to say is I'm going to already have computed the optimal way to do all of those size 3 subsets, right? And so all I have to do when I'm considering this size 4 join is look at all the size 3 subsets and then figure out how to add the fourth relation onto it. Okay? So, for example, right, if I'm doing A, B, C, and D, I already know how to join. I know the best way to do A, B, and C. Okay? I know the best way to do A, C, and D, okay? And I know the best way to do B, C, and D, right? And that's all, these are just all the size 3 subsets of A, B, C, D, right? So I know that once I compute it, and I will, in the dynamic programming algorithm we're going to build up, I'll have already computed the best way to do each of these, right? So then all I have to do is figure out the best way to join this with B, the best way to join this with B, and the best way to join this with A, right? Whatever this is, whatever this plan is, I just figure out the best way to join this with each of these additional relations, okay? And then I take the best one of these, and that's going to be the best way to do A, B, C, and D. You guys kind of see that? We're going to like actually write the algorithm down in a minute, but I want to make sure you guys kind of have the intuition before we go through the algorithm. So are there questions? What's that?
A, B, and D, but yeah.
Oh, A, B. What did I mess up? I missed A, B, D. Sorry. Okay, thank you. A, B, and D. Okay, join. Okay, good. Thanks. All right, so good. So now let's actually look at the algorithm, and hopefully it'll be pretty clear. I handed out one instance of the algorithm last time. I'm going to actually go through two different formulations of the algorithm, one of which is a little bit more kind of set-oriented in nature, and one of which is a little bit more like imperative, like if you were going to write a program to do it in nature, just so you guys kind of get a feel for it. Okay, so our algorithm, we're trying to compute the optimal way to generate every subjoin, and like most dynamic programming algorithms, the way we're going to do this is we're going to start by sort of considering increasingly larger subsets. So we'll first consider all the size 1 subsets, and then we'll consider all the size 2 subsets, and all the size 3 subsets, and so on and so forth. And we'll reuse the results of the computation for the smaller subsets when we're computing the larger subsets. All right, so if we have this set R of our relations to join, we're just going to consider this index I that ranges from 1 up to the size of R. Okay? So this is just telling us which size subset we're working on right now. That's I. Okay. And then for every subset S of length I in R, right, we're going to consider this in a loop. So if I is 1, then and we've got 4 relations, then we're going to consider these 4 subsets A, B, C, and D. If I is 2, then we're going to consider all size 2 subsets, and so on and so forth. So S is just one of these size I subsets that we're currently considering as we run through the algorithm. So the optimal way to join S, right, is to compute this, is going to be A join S minus A, where A is some relation in S. Okay, so if I'm considering the set, right, A, B, and C, right, then I'm going to consider all the possible choices of little a. So little a might be big A, little a might be big B, and little a might be big C. So I'm going to consider all 3 possible cases of this, okay? And I'm just going to compute the sort of, so the best way to join A, B, and C is going to be to, compute the best way to do B and C and then add, it's going to be exactly like we said here, the minimum of the best way to join B and C and then join that with A, or the best way to join A and C and then join that with B, or the best way to join A and B and then join that with C, okay? So all we do is find this relation A that minimizes the cost of the following sum, which is the cost to compute the join of S without A, plus the minimum cost way to add A into S without A, plus the minimum access cost for A. So I have to, like scan A or do an index lookup on A or something, right? So it's this this is the expression, and I want to find the A that minimizes. I want to find the A that minimizes this for each of these subsets S. Okay, and because I'm considering these increasingly large subsets of S, this cost of optioning of S minus A, will have already computed by the time we get here, right? So we already know the answer to this. We've memoized it in dynamic programming speak. We've saved it off, and we can just reuse it. Okay? So to look at this, this is what I handed out last time. To look at this in code, hopefully to make it a little bit more clear, we've got R. We consider all these size I subsets. We can consider all linked I subsets of R, which is S, and then what we do is we initialize this variable, which is the optimal cost of doing S and the optimal way to join S. And then we consider all these subsets A that are in S, okay? And the cost, and then for each of these subsets, we compute this cost, which is the best way to join S to do S without A, plus the minimum cost to join A into that S without A optimal join plus the minimum access cost of A itself. Okay, and then if this cost is less than the optimal cost we've computed for this set so far, we just update the cost. Okay, so at the end of each iteration of this inner for loop, what we'll have is the best way to join, we'll computed the best way to join all, to do all the linked I subsets of R. You guys want to see an example? Maybe that'll make it clear. I know it's a little bit hairy, but hopefully it'll be pretty clear when you see the example. Okay, so let's go back to our ABCD example. So the algorithm again is going to proceed in rounds of increasingly larger subsets. So we'll start off by computing the best way to access each one of the base relations, A, B, C, and D. Okay, so this is like the base case. Then what we're going to do is consider all the size 2 subsets. Okay, and all the size 2 subsets, well, the only options for A, B is either I can do A as the inner and B as the outer, or B is the inner and A is the outer. Right, so I have only 2 options for each of the size 2 subsets. Right, and I have to consider, in this case, these 6 size 2 subsets. Right, and I just compute the best of these. So the answer for each one of these A, B, it's either going to be A, B, or BA, and I just compute it and I save it. Right. Okay, and then I go on, I do the same thing for the size 3 subsets. So for the size 3 subsets, I have to do this kind of removal thing, right? So I'm going to, for the subset A, B, C, right, I'm going to remove A, and then I'm going to compare, A join BC to B join CA. And similarly, I'm going to remove B and compare that, and remove C and compare that to these 2 options, okay? And then I'm going to take the best of these 1, 2, 3, 4, 5, 6 possible ways to do A, B, and C, and I'm going to save that. That's going to be the best way to join A, B, and C together. Okay, and then I repeat for all the other size 3 subsets, A, B, C, A, B, D, and B, C, D, right? And then finally, to do A, B, C, D, well, all I have to do is consider, removing A and comparing that to the best of these, each of these alternatives here. Right, so at the end, I just compare each of these 8 plans and I get a final cost. Okay? Yeah?
Doesn't that not match the left equal?
Yeah.
Okay, so you're right, actually, that this what I've enumerated here is more than we needed to enumerate here. So we didn't actually need to consider, we only needed to consider these plans where the new relation I was adding was on the right side. So it's actually, the complexity is somewhat decreased because of this. Like I only have to consider, instead of having to consider, like here, if there are 3 relations in this, I have to consider, or if there are n relations in the join for each subset, I have to consider 2 n plans, and actually I only had to cost n. I would have only had to cost n plans. Yep.
What is the optimal way to join A first and to join C and then to join both A and CD?
Okay, that's not a left-deep plan. So it turns out that is, so people have shown how to extend this dynamic programming algorithm to consider that case, and the algorithm you end up with is 3 to the n instead of 2 to the n. Okay, so that's, but we're not going to go through the details of it here. Okay? All right, so good. So does everybody feel like they at least kind of have a sense of how this dynamic programming algorithm works? So now let's, what I want to do is think about, okay, what was the complexity? So what did we buy by doing this? So, I already told you what the complexity is, but let's see if we can understand why the complexity is 2 to the n. So the sort of key observation, right, is that what we're doing at the core of this thing is enumerating all of the subsets of these, the relations that we had, right? So I'm computing all the size 1 subsets, all the size 2 subsets, all the size 3 subsets, and so on and so forth. Right? So this is the power set, right, of this input set that I had of relations. Okay, the size of the power set is 2 to the n. If you want some intuition about why it's 2 to the n, you can think of this as enumerating all of the strings of size, if I have 4 relations of 4 bits, right, like or 4 values. So it's like you can. So all the size 1 subsets are like that, right? All the size 2 subsets are all the strings where 2 bits are set in it. All the size 3 subsets are all the strings where 3 bits are set, and all the size 4 subsets are the set where 4 bits are set, right? And so you can sort of see that effectively what we're doing is writing out the power set is equal to the sort of all of the binary strings of size is enumerating all of the binary strings. That's the size of the power set, is all the binary strings of the same number of entries in the set. And hopefully it's obvious to you that this is 2 to the n, right? Because there's 2 to the n possible such strings, okay? So we've got 2 to the n sort of iterations, or 2 to the n, possible, if we go back to our algorithm here, 2 to the n subsets that we end up enumerating, right? And then you can sort of see within each one of these subsets, we do work that is at most size n, right? Because we do this for a in S, right? And the size of S is upper bounded by n, right? S is, in the last iteration, S is equal to n, right? So the complexity of this is basically n 2 to the n, okay? Total, costs. So we have to do of these cost computations, we do n 2 to the n of those, right? And just to give you a sense to make it really clear, this is a huge win, right? It's like if n is equal to 12, n 2 to the n is 49,000 versus 49,000 versus 479 million if you consider n factorial. Okay, so we reduced the amount of work we had to do by a huge amount by sort of doing this pre-computation. And obviously, these things are on a completely different scale. So if you go into the 32nd or something, this is only 4 billion. And as we said last time, this is like 32 factorial with some number bigger than the number of atoms in the universe or whatever. So it's a win. As I said last time, it still is possible to encounter query plans that are not really tractable to do in this kind of world. I mean, 2 to the n is still a pretty big number, and the amount of work we're doing here isn't totally trivial because each of these cost evaluations requires me to kind of consult the optimizer or something. I have to go do some lookups in some tables in order to estimate the total amount of work that we're going to do. The Cylinder optimizer is pretty simple, but if we are talking about what Postgres does, right, the way it does each one of these cost computations is to do this, work with these histograms and these most frequent values, and it's a non-trivial amount of arithmetic you have to do for each one of these cost computations. So, and real query plans, sometimes you might be doing 15, 20, 30 relations, so you can get into situations where you need to do something other than use this Cylinder algorithm. And as I said last time, Postgres has a genetic optimizer that it uses, but there's lots of different heuristics, optimization heuristics you might apply to solve this problem if you want to. Okay, so I just want to say one last thing about this interesting orders thing. So I kind of pointed this out before, but it's possible, first of all, that the best way to join D might be to do a merge join if I have a way to access D in sorted order. So if I can, in the sorted order of the join relation, and so if I can produce A, B, C in sorted order, that may be beneficial to D, to the join with D. And so therefore, this optimal substructure property might seem to not hold. Furthermore, the optimal plan may be to use a sort merge join in order to produce the results in sorted order at the end of the query plan. So if the query has an order by a certain expression, for example, and that expression is one of the join attributes, it may be preferable to consider plans that produce data in the in sorted order, so that I can avoid having to do this final sort or order by expression. So what the Cylinder optimizer says is kind of a cute trick, which is that when you look at the query in advance, you can compute all the so-called interesting orders, right? So for every one of these, like for example, D for the subset D, for the subset ABC join D, one possible interesting order would be to produce the output in sorted order of the join expression with D. In addition, an interesting order might be if there were an order by clause on some other attribute E to produce the output in sorted order of E. And then what you do is at every one of these steps, instead of just computing the optimal way to join S and the optimal cost for S, you compute not only the overall optimum, but the best way to produce the output in in each of the interesting orders that you computed in advance. So if there's 2 or 3 interesting orders or K interesting orders, then you compute K optimal. You start to run K iterations of this inner loop. Okay? So what you end up with is an additional factor of k in front of this, which is the number of interesting orders. And this allows you to do things like consider plans that produce data in sorted order, even when the sort of join ordering isn't totally optimal. Okay, so are there questions? I know that was pretty whirlwind. The slides are online. Look through the algorithms. Hopefully the combination of the example and the slides will kind of help you to understand what's going on. Yeah?
Can you remind us where the N comes from? So it's KN.
Oh, this N? This N is just because, I mean, this isn't, it wouldn't be there in big O notation or whatever, right? But you do have to do, for each of this inner loop for A and S, right? Sorry, for there's several loops here, right? But I have to do, for each one of these length I subsets, right? I have to do work that's proportional to N because I have this for A and S. Right, and this S is the current subset I'm considering, so the size of S in this inner loop is upper bounded by N. It's not actually equal to N, but if that makes sense. Any other questions? Okay, we'll take a 5-minute break. We'll come back at 3:10. So we're enumerating all subsets. That's what it comes to. That's the two outermost loops are enumerating all possible subsets, right? And then for each one of those, we have to do this. So we've got the N passes through that outer loop, and for each one of those, we have to do. And then the K is if we want to maintain so-called we do an additional pass some particular sort of okay. Oh, right. Sorry, I didn't. Okay. So, you're asking. Oh, Twitter makes a wonderful example. It's totally fine to reuse some of the want to add something on top of this. So as long as you well, I mean, for example, thinking about like if you want to do something on the Twitter screen, add something database operations, there's a whole bunch of papers that look at stream processing, evaluating that Twitter data set based on real world, something like some research paper history and see how it there's some thing. Yeah, like so suppose you want to, I don't know, take something real quick, like study. How would you go about this is fine, but it's not. I don't have a problem.
I keep trying to look at things and I can't. My brain is working on other things right now.
Yeah, so I'm like, okay, I can't work on a project like less than an hour to do it. Like, I'm like, okay, it's not like I can get to the project left over. Like, I'll know the time I'll get with this already. So I feel like it takes forever to do it.
Because like, I feel like, you know, as you go further in your education,
All right, let's get started, guys. So, the reading I assigned today is this paper about so-called self-tuning database systems. But what I really want to get out of it is to think about this problem of automated physical database design. Okay, and what I mean by automated physical database design, and what the authors of this paper and the papers they refer to in the reading really mean, is two things. One is to automatically select indexes. And to automatically select materialized views. Okay, so we'll talk about, I'll remind you what a materialized view is in just a minute. But so the intuition is there's, in order to get good performance out of a database system, right, it's great to have an optimizer that can compute an optimal plan. It's great to have these fancy cost models and all these statistics, but ultimately a lot of the performance of a database system depends on having the right physical database design, like the right set of indexes that have been created, right? And if you get the indexes wrong, then the performance of the system is going to be slow, no matter how great your optimizer is, okay? So what's wrong with, so the way that this is like, traditionally been viewed is that there's some database administrator who's going to be responsible for creating good indexes on the data. So what's kind of wrong with that viewpoint?
They have to guess what's going to be accessed.
Yeah, you have to guess what's going to be accessed, or you have to be, and the administrator has to be very proactive, right? Like they have to be paying attention to what's happening with the database and what runs slow. I think traditionally the way this works is that people run queries and then their queries start running slow and then they go bitch to their database administrator who figures out what indexes to create or how to make their queries run faster, right? And this is probably the way, those of you who've worked in an organization that has a large database works. Like, if something isn't fast, you figure out who to complain to and they help you make it go fast. So I think in order to understand this, so this particular paper is written by a research group at Microsoft, and they're kind of the natural group to do this. So Microsoft is, they're a smaller player in the relational database market, but they do super, super well in the market of like smaller businesses and small, lower end databases that are not giant enterprise things that are running back end of Walmart, but the 10 to 100 person company that needs to maintain a database for something, right? So this Microsoft SQL Server is sort of the natural thing you would Windows users at least would use as a database product in order to store their data. And so in the 90s, they got a lot of market share, and they still have probably 20% market share in the relational database space, but it's at the relatively lower end at smaller customers. And those are less sophisticated customers who are less apt to have, you know, a DBA on hand who's going to be great at making these kinds of decisions. And so they really wanted to focus on this, you know, making the database friendly and easy to use. And so the idea is we're going to automatically do this, and we're going to maintain it as the database runs, and we're going to, you know, try and kind of look at the queries that users are issuing and figure out what the right set of things to create is. Okay, so let's come to this. Let's talk quickly about materialized views, just so you guys remember. So a materialized view is just a view, so it's a expression defined over a table that gets physically stored as a table. It can have indexes stored on it, and it's maintained as the underlying database changes. Okay. So to give you an example, you know, if I have a table like sales, right, I can create a materialized view which is sales by date, which looks like this. Okay, so this is the sort of pre-aggregated sales by date, right? So I went from a table of every individual sales transaction to some sum and count of sales by, you know, date and product, right? And now you can imagine that there's a bunch of queries you might ask on this, like what was the most popular product sold on a particular date, or what's been the most popular product over time, and so on and so forth. Okay, so again, the sort of context here is that in the 90s, people worked really hard at making this materialized date view thing work in relational database systems. So in particular, they developed these kind of two key properties, which is that these views are kept up to date as data is added or modified in the database. And the views are chosen automatically by the optimizer. So people worked out the algorithms so that when you ran a query, an arbitrary SQL query on the base table, not on the view, but on the sales table, the database optimizer would automatically choose the sales by date materialized view when it was appropriate to choose it. Okay, so you can see sort of how powerful a tool this is, because now as a database administrator, I can choose a set of these materialized views to create, and they will magically make potentially a large subset of the queries that the database system has to run go faster, because I'll have pre-computed a significant part of the answer that I need. Right, so if I want to find the most popular product on a certain date, in the base relation, I would have had to go through and scan, you know, maybe thousands of records from, you know, every date in order to kind of count the number of, you know, products sold on every one of these dates. In this materialized view, I could look at a much smaller number of records, right? And furthermore, I can create separate indexes, and I can separately cluster this materialized view from the base relation. So I might not have an index on product ID in the sales table, but I might have an index on product ID in this materialized view. Okay, so this is a very powerful kind of physical database design tool, but it's also one where you can imagine that it's hard for a database administrator, you know, given a log of thousands of queries that have been run over the database system and millions of queries even, to sort of figure out which are the best ones to create materialized views for. And we can't create every possible materialized view because there's clearly a huge number of them, and they do take up storage space, right? They're not free to create. So the other thing that, you know, so hopefully it's clear why, you know, this materialized view selection problem is kind of a tricky one. We can't create all of them. There's a huge number of them. The other question you might ask is, well, what about indexes? I mean, why do we really need an index design tool? There aren't that. It doesn't seem like there are that many indexes that you would want to create. So the thing to realize, or the sort of argument that this paper makes, which I think is a good one, is that one thing that at least Microsoft SQL Server was able to, they added to Microsoft SQL Server and most other relational databases kind of added to them are these so-called covering indexes. So a covering index means that if I you know, have a query that's looking up, for example, you know, it's a query that fetches, you know, say, two attributes, A and B, from a table. If I have an index on A and B, I don't need to go into the base relation to do that. I can just answer the query using that index on A and B. Okay, so this makes indexes kind of like materialized views now, because if I, you know, have an index that has all of the attributes that I need to answer the query in it, I can just directly answer the query from the index without going down into the underlying heap file, right? But now suddenly I want to start to materialize these indexes with multiple attributes in them in order to cover popular queries. And now you can see that with multi-dimensional, so multi-attribute indexes, you know, there's this exponentially large number of such indexes that I might create. Right? So if I have a table with n relations, it's the same subset enumeration problem. I have 2 to the n indexes for a table with n fields. Right? So I have this exponentially large number of such indexes that I might consider. Okay, so this is kind of the context, right? I've got this huge number of possible materialized views I might create because I can materialize anything I wanted, and I've got this huge, space of possible indexes I might create because I might want to cover any query with indexes, right? And so which one should I create? Okay. So if I gave you guys this question.
Is the goal to create these at table creation time or after some number of queries have been observed?
Okay, good. So that's a good question. Is what is the context that we're operating in? The intuition here is we want to do this. It's going to be workload sensitive, right? Because it sort of doesn't make sense to talk about. It probably doesn't even make sense really to talk about what indexes you want to create unless you have some model of what the queries look like, right? And if we're going to build a tool that's going to do this automatically, probably the most sensible thing to do is to look at a log of queries that have been run or a log of queries that go slow and use that log in order to drive which of these structures to create. Yeah?
How can you keep up the data update with
How does this update problem work? So the view update problem in general is an NP-hard problem. For certain classes of materialized views, it's possible to solve this problem efficiently. So there are sort of 2 choices, right? You can, if you can't do this, of course, you can recompute the entire view every time the data changes. That's going to be a bad idea, but you can always go back to the base data and compute it. For a query like this one, right, you can probably, if I gave you the problem of updating this query, this particular query, you could probably work out a strategy for it, right? So for these simple aggregation queries, where you're only considering inserts and deletes, right, it's not really that hard to go, update the sum and update the count for the appropriate bucket when a new record arrives, right? And so the cases where this is hard are these cases where the materialized view is missing a key attribute that would allow you to figure out which record the update was supposed to be mapped into, right? So if I project out the list of all of the I project out the list of all the products from my database. So I create a materialized view, which is select product from database, right? And then I delete a specific entry from the database, figuring out whether that should cause that product ID to be deleted from my materialized view is a completely intractable problem, right? Because I don't know whether that was the last instance of that product that I just deleted or not, right? So I'd have to scan the whole table in order to figure this out. I basically have to recompute the view in order to do this. So the problem is it's sort of a non-trivial, and there's a long theory literature on what are the classes of these views that we can automatically maintain. But the database systems have technology, have the ability to tell you whether a given view is something they can maintain or not. Okay. All right, so I give you this problem. Here's your problem. So maybe let's just consider the problem of indexes. Materialized view sounds hard. So I give you a workload, and I say, compute what indexes should I create? Anybody have any suggestions? So first of all, the thing to realize is, and I think it's important to realize this just because sometimes it's easy to get caught up in these people are super smart and they're famous database researchers. Of course, the solution they came up with is going to be really awesome and sophisticated and way better than anything I can come up with. Actually, the solution they come up with is probably kind of like the solution you're going to come up with. And the kind of thing to realize is this is this giant exponentially large search space. Anything that anybody comes up with is going to be some kind of heuristic that's going to do something moderately intelligent to search through this search space. And there's a lot of such heuristics you might propose. So I don't know. What do you guys think? Yeah.
We can start with whichever indexes have the most distinct results. If something has the same value over and over, you can always create an index. So you can start with the most distinct indexes.
Okay, so this is one that's looking at the distribution of data. I think and it probably is true that there are going to be, depending on how the data is distributed, you might get more or less benefit from a given index. I think it probably makes more sense to start by looking at the queries that you have available, right? So, does somebody else want to suggest a different alternative? Yeah.
Look at the workload and index the top K columns that are
Okay, good. So I might like just say what are the most popular columns, and I can create an index on every one of them, right? And this probably will get you some part of the way there. The thing that this may not work for is that it breaks up it's sort of, if there are groups of columns that are frequently co-accessed, right? We may be able to use this covering index trick to make queries like that go fast. And that was an explicit intuition that they had. So they don't want to just consider the frequencies of the single attribute accesses, but they actually want to compute the popular, the groups of columns that get co-accessed. But basically, this is what we're going to do. We're going to look at the workload. We're going to look at the sets of columns that occur in that workload, and then we're going to somehow choose which of those sets we should create indexes on. Okay. And actually, the intuition for materialized views is going to be, turns out that their approach is not going to be that dissimilar than that. Actually, we're going to kind of look at the queries. They're going to take they take the queries and they kind of abstract them a little bit. So they consider generalizations of the queries where they, for example, removed specific equality predicates in the where clause. But they basically take all the queries that occur and they find the queries that sort of occur. So for a given query that ran, right, it's pretty obvious what the best materialized view for it is, which is to create exactly that query's materialized view that computes exactly the response of that query, right? And if you computed that and stored it, then that one query would have been fast, right? And if that one query ran a million times, that might be the right materialized view to produce. But in reality, you might want to produce something a little bit more general, more general materialized views that cover more queries, but maybe less perfectly, right? And so they're going to sort of figure out how to generalize these things a little bit. So let's kind of write out the key steps that they came up with. Just go through. Okay, so so the first step that they talk about is what they call pruning. And pruning is really about reducing the input. Okay, so the observation is, like, you're running a production database system for a while, you're going to accrue millions of queries that get run against the thing. You don't really want to consider all of those queries, because many of those queries may have only been run once or a small number of times, right? So they call this frequent item set mining. Basically, all that means is look at the queries, compute the queries that get run most, the top K queries that get run most frequently, and use that as your set of queries that is your workload, right? So we're going to use this to produce a query workload, which is going to be the sort of K most frequent queries. Okay, so we take this network, so the first thing we do is we just get this set of K most frequent queries, and then what we're going to do is feed this into what they call a candidate selection module. And this is, it's actually, they have a pretty cute trick, which is, or I mean, maybe it's a cute trick or kind of a brain dead idea, but in retrospect, I think it's a good idea, and it kind of surprised me the first time I saw it. So they say, let's not, at this point in this algorithm, let's not worry about trying to pick the optimal set of things, okay? Let's just, for every one of these queries in our workload, let's not try and pick, let's not try and constrain down the sort of set of things too much at this point. Like, let's just, for every one of these queries in our workload, let's figure out what the best thing to do for each query would be, right? So for every query, I can look at that query, and if I want to compute the best index for the best materialized view, I can, for a given query, it's pretty easy to answer this question, right? Because, for an index, so this is for each query, compute the best, one index or two materialized view. Okay, and to compute the best index for a query, well, my query is like select A, B, select some set of fields where something, right? I mean, by using this kind of covering index idea, the best index for that query is going to be the index that contains all of the fields, in the ordered in the sort of order, first of the, in where predicate order. So if it's select A, B, C, and D, where D, A, B, and C, where D, then I want my index to be first ordered on D, and then I want to stick A, B, and C into that index because I'm going to be able to use this as a covering index to pick up A, B, and C fields. All right. For a materialized view, it's even more trivial because the optimal materialized view for a given query is just the query, right? So at the end of this candidate selection, what I have is this huge number of possible indexes and materialized views I might create, one for each of my k most frequent queries. Okay, but these things are all going to be overlapping. Like I might have one index that has A, B, and C, and another index that has B, C, and D, and I might have one materialized view that has where attribute is equal to X, and another one that's exactly the same query but where attribute is equal to Y. These things are all going to be overlapping in some way, and I haven't done anything that can screw down this way. Okay, so this candidate selection is kind of a stupid step, but it's a cool step because I sort of, for every one of these things, I think if I could, if I wasn't worried about updates, if I was only worried about queries, at this candidate selection step, if I were just to materialize each one of these structures that was produced, and I had infinite disk space, then this would be the optimal thing to do, right? But I don't have infinite disk space, and so what I need to do is to somehow kind of prune this down a little bit. So there's two more steps. So they still don't exactly prune yet. They do what they call merge, okay, which is to consider so what the merging step basically does is to take all of these candidates that we produced in the second step and figure out for every sort of pair of candidates whether there's a merged index or a merged materialized view that is almost as good as the one in that we enumerated in step 2, but that would be smaller than the size of the two things that we merged from, right? So to give you a simple example for indexes or for views, let's consider the case of views. If I have two queries, two views like select A from T where B equals C1, and I have a second query or second view that I created in step 2, which was select A from T where B is equal to C2. Well, if I want to merge these two together, there's a couple of different ways I might merge them, right? Like I might merge them by eliminating the where clause altogether, right? I might just say, for example, select A comma B from T without the where clause, right? Or I might take the kind of union of the where clause. So I might merge them into select A comma B comma C from T where B is equal to C1 or sorry, it doesn't really matter. I don't see here. Or B is equal to C2. Right? So I can merge them in a bunch of different ways, but I can generate these kind of merged plans. Do you guys kind of see that? So again, this is a heuristic about how I might merge these things, but I can do it. Merging indexes is very similar. I mean, I just say if I got two indexes, A, and one query wants A and B, and another query wants B and C, then the query 1, and this is query 2, right? Then the merged one might be, A, B, and C. Okay. So this particular index is not going to be it's going to be pretty good for query 1. It's not going to be as good for query 2 because I have this A at the beginning of the index, but I can use this index to help me answer either of these queries, and this index covers both of these queries, and so maybe it still is a pretty good choice, and hopefully will be smaller than either one of these things. All right? Okay, good. So at this point, the merging step, we don't actually consider. Wait, this is all. We're not actually materializing anything yet. We're trying to decide what to materialize. But in the set of possible things to materialize, we don't yet eliminate anything. So we consider everything we generated in the enumeration step and everything we generated in the merging step. So we're going to generate this huge number of possible candidates using merging, okay, and all the base ones that we considered, which were the optimal ones. Okay? And then finally, we get to this step, which is the, they call the enumeration step, which is the one where we actually make decisions. Okay? And this is where, of course, all the kind of secret sauce is, and it's where the most hand-wavy heuristics come to bear. Right? So, I mean, at this point, you can sort of say, well, this is a fairly principled approach. I mean, you believe that the optimal approach might be in here, and of course, there's some, kind of guessing games about how you merge views together, maybe that could affect performance, but it feels like a pretty good approach. But then, when you have the choice of actually choosing which ones to enumerate, well, this is where the heuristics come to bear.
Question?
Hold on just a second.
Yeah.
Yeah.
Why would the merged view, for example, be smaller than the two with merged?
Okay, so, well, where B's, okay, so in this particular case, it might not be any smaller, right? So, this might not be a win, but this is a candidate merging, right? So what we're going to do, you'll see, is we're going to basically consider replacing, I mean, there are several different algorithms, there are two different algorithms we're going to talk about, but in one of the algorithms we're going to talk about, we're going to consider replacing the two base relations with their merged result. And the sort of benefit, we're going to do this cost-benefit analysis where we're going to consider how much reduction in space we got versus how much slowdown in speed you got. And we're going to kind of compute this ratio, and we're going to use that ratio to decide which thing to materialize, which of these things to materialize. Okay? So the enumeration step is the sort of problem in the enumeration step is we've generated all these candidates, a huge number of candidates, right? And what we need to do in the enumeration step is compute from all these candidates which ones should we materialize that will fit into some storage budget, right? So find a subset of candidates in some storage budget. Okay, so I might want to say, I don't want to use more than twice the storage that I use to store the base relations to create these views and indexes. So find the best set of candidates that you can create that can fit in the 2x the base storage of all the tables in the system, right? So the user supplies the storage budget, and we have to search through the space and find it, okay? So you could formulate this as some optimization problem. I mean, in fact, people have. You can think of this as a linear programming problem, and throw this at your favorite solver. That might be one way you can solve this. What they propose in this paper and what they've done in their work are some sort of even less principled algorithms than that. A so-called bottom-up approach and a so-called top-down approach. Okay. So the bottom-up approach is the easiest to understand. This is just a greedy algorithm. Okay? And it's greedy in the sense that what I do is I want to pick something to materialize. So I just pick the thing that has the highest value. Okay? And I assign a value to something like its value is equal to something like the change in the expected change in the runtime of the workload divided by the space that the thing that I'm going to materialize is going to create. Right? So I've got this giant set of things that I enumerated, and I just picked the one that will most increase the runtime of my workload, relative to the amount of space that it occupies. Right? So if I have some very tiny index that I can create, it will make 50% of my queries go faster. That's going to be a great choice, right? Whereas if I have some materialized view that makes one of my queries run really fast, but uses up my entire storage budget, maybe that's not a good choice. So I just basically pick the thing that has the highest value, and I just do this. Greedily over and over and over again until my storage budget is exhausted. Okay, it's like a pretty trivial algorithm. All right, so the top-down approach is a little bit more interesting, but again, it still is pretty simple. So in top-down, The idea in top-down is that instead of kind of building up from nothing greedily, in the top-down approach, we're going to start with the optimal design. That is, in particular, we're going to start with this everything we produced in this step 2 here. And then we're going to consider replacing things in this step 2 with things that we generated in the merging step, this step 3. Okay? So we're just going to take pairs of things that we produced in step 2 and consider replacing them with things in step 3 until we get underneath our storage budget. Right? So if we do everything in step 2, we know step 2 is optimal, but we don't have sufficient storage budget for it. And the idea is we're just going to remove things from our optimal design until we get something that fits in our storage budget. Does that make sense? So all we do is we're going to remove, we're going to replace pairs of these candidates from step 2 with merged candidates with sort of like what we produced in step 3, okay? Or what we produced in step 3. And we're just going to repeat until we're under, repeat until the budget is satisfied. Okay, so we just repeat this replacement until the budget is satisfied. Okay, and then of course we're left with the question of which pairs of candidates should we consider. Does anybody want to propose pairs of candidates to consider? Yeah. Okay, so I wonder, I could replace the 2 with the lowest value with something else, but I guess the question is, you know, so I think what you want to think about though is not only do you want to replace things that are don't add a lot of value, but you want to replace them with something that sort of does you know, maintains their value as much as possible, right? So like kind of what I want to do is like you know, find replacements where I don't decrease the value I don't decrease the value of the 2 things very much when I replace them with one of these merged things, but I significantly decrease the storage space, right? So how might I, so I can sort of use something that's like this, right? Where what I want to do is I want to minimize, you know, how to choose. Well, I want to minimize this delta t over space change, right? So if I you know, have a replacement for a pair that's 1 second slower and saves 100 megabytes, right? That's better than a choice that's like 10 seconds slower, but you know, saves me 10 megabytes, right? So I want to pick the sort of one of these that has the smallest ratio of time increase, right? So this is the time increase to space decrease, right? So presumably by making this replacement, I'm decreasing the amount of space, but I'm making the overall expected runtime go higher, right? So I kind of want to minimize this, find a pair to replace that minimizes this one. And I just kind of do this over and over again until I fit the space budget. And again, this isn't optimal. I mean, because we're sort of looking pretty myopically, we're only replacing one thing at a time. We're not, you know, considering a global optimum of all the things we might replace, but you know, they show that heuristically this works pretty well. Is there a question?
When you're finding the merged things in step 3, do you also find like merges of 3 things and 4 things and stuff?
Yeah, that's a good question as to like how far you look in your merging. I think what they really intend is that this actually, you're going to compute the possible merges in each iteration through this loop. So what you'll do is, you know, in this loop, you'll have this, you know, you'll have this optimal things. For all the pairs of optimal things, you'll consider all the merges you can find, and then you'll do this replacement, and then you'll insert that replacement back into your set of optimal things, and then you'll recompute possible merges even with that replacement, right? So that you could merge something multiple times together in that way. That's sort of how their algorithm ends up working out. Yep.
Does step 2, if the queries are similar, does it still compute index materialized view every time?
It's just like, it's a brain dead step, right? But the thing is that we'll kind of, this will kind of, I mean, obviously if the queries are identical, right, you wouldn't include in your candidates multiple copies of exactly the same indexes, right? So if like the covering index is ABC for query 1, and it's also ABC for query 2, you'd only have one instance of covering index ABC, right? And you would consider that when you considered the affected runtime, right? Like there would be 2 queries that both benefited from ABC, so you'd want to take that into account when you compute your runtime.
It's just weird because we keep calling this optimal, but it actually doesn't, like there's no speed up increase, you still have to do all the computation. Like if you actually compute an index materials view for every single query, then...
Okay, great. So this is the point I want to come to, which is, okay, how do they actually do this? Because you're right, that if what we had to do was create all these things, it would be a total frickin' disaster because we'd spend all of our time creating all these things, right? So this is the other kind of thing they proposed, which was an interface to make this work, right? So because I don't want to compute all these, what I need is a way to ask, what would the benefit or the cost, the effect of creating this index be or this materialized view be? I don't want to actually create it, but I want to have a way to ask the optimizer how I would create it. Okay, so they proposed this, this optimizer change, which is so-called what-if analysis. So they proposed that the optimizer, they made extensions to the optimizer so that you could ask it questions like, what if I had this materialized view on this table? What would the runtime be? Right, so you can think of, if you like, we saw those statistics tables that Postgres maintains last time. You can think of this as basically they made it so that external programs could insert hypothetical tables and hypothetical entries into those statistics tables so that you could run the optimizer on tables that didn't really exist in the system. Right, and so then the optimizer could say, well, if you had this materialized view available to you, the effect on all these queries in your query workload would be the following. Right, and so then you can invoke the query optimizer, once for every query in your workload for every one of your candidates that you're evaluating and figure out what the benefit of it would be. Right, so this is still a non-trivial amount of computation because the query optimizer itself, as we've seen, is a complicated thing that does a lot of work when you run it, but at least it's better than actually physically materializing each one of these possible structures and running the real queries on the real physical structures. Right? So there's this cute trick, which is that we can kind of fool the optimizer into telling us how to evaluate the cost of all these different things. No other questions? Okay, so I know I went through this at a pretty high level. Hopefully you get the feeling that, and I want to kind of emphasize this, there's a lot of different ways you might do this. This paper has one good proposal for this, but it's really just a proposal of one research group. The paper does a nice job of describing all the other research projects that have tried to do similar things, so it's a kind of a nice tutorial paper that gives you a lot of background in the space if you're ever finding yourself wanting to build one of these things. But I think it's important to realize that database systems now include not only this query optimizer, but these physical storage and layout optimizers that can do surprisingly clever things with the physical representation of data on disk. So the paper talks about some other things that people have developed in the physical database optimization space. So in particular, people have used these kinds of tricks to do a number of other kind of physical optimization. So one thing, for example, that people have worked hard on is this problem of progress estimation. So it's kind of related to physical design and optimization, but this idea that as a query is running, you might want to have the ability to emit how much progress you've made in running through that query. That means you have to have extensions to the optimizer to understand how much of the query plan has been evaluated and how far you are through the query plan. Because those optimizer cost estimates, as you guys probably have seen, don't necessarily map directly into real time. So you can't sort of use the optimizer cost estimate to estimate how much longer you have to evaluate a query. You need some other thing to sort of, as the query is running, actually produce estimates about how far you are through the query plan and how much longer it's likely to take. So you should read through the paper because I think it has a lot of cute tricks like this that are sort of nice things to have in a database system. All right, so with that, let's wrap up. No class next Monday, so I'll see you guys on Wednesday. Good luck with problem set 2, and enjoy the holidays.